So I'm recording the class now. And let me just share screen. Okay. So, okay. And one other thing, next week also we have Professor Gassard, who is giving 2 lectures continuing about approximation algorithm that we have today. Just be there on time. That's important. Let me. Good. So, any question? So today we are talking, today and the next few sessions, we are talking about approximation algorithms and inapproximability. And these are the lower bounds for approximation algorithms. So these are, I mean, a very general set of problems, approximation and inapproximability, and you can have a class on that. But here again, we are talking about the concept, what is an approximation algorithm. We give some examples of that. Especially today, I want to give you a general ideas about approximability of minimization and maximization problems. And then we will continue with the approximation preserving reductions, etc. next week. So good. Here, first talk about the approximation and inapproximability. So this is actually approximation and inapproximability. So that is one way. The other set of problems are fixed parameter algorithms. So these are the fixed parameter algorithms. These are the 2 ways to somehow attack or cope with NP hardness. So for the problem which are hard, we cannot get the exact solutions. So then in that case, we need to but we need to solve them. These are very practical problems. Actually, lots of practical problems are NP hard, but still we need to solve them. So these are the things that approximability and inapproximability becomes very important. And here there are 2 approaches, the fixed parameter algorithm and approximability and inapproximability, that we will talk about both of them. But today we are talking about the approximability part, and the fixed parameter we talk later in the course. And so what is the idea for approximation algorithm? Is that, okay, we cannot solve the problem, let's get approximately correct solution. So the running time of this algorithm should be fast, in a sense they should be in polynomial. So we want all this polynomial so these are all polynomial time algorithms that we are talking about. So in the fixed parameter, actually, so this is the interesting thing. Here, we are somehow relaxing on the fact that approximation might be, so we may not get the exact solution here, but the running time should be polynomial. So running time should be polynomial. In fixed parameter algorithms, actually, we have exact solution, but the running time is exponential, but it is exponential. For example, so this exponential, but I mean, essentially, you don't want to get 2 to the n if the input size is n. You want to get the running time is something like 2 to the k times n, where k it is called the parameter. And for lots of practical case, k might be much less than n. In the worst case, k can be order n, so it is still exponential. But for lots of practical problem, k might be smaller than n. In this case, would be, I mean, much better, because it can be potentially 2 to the k. I mean, this is in general 2 to the k n to the c for some constant c. So that's essentially for fixed parameter algorithm that we will talk about. 2 to the k n to the c, and here k is the parameter that we will talk is the different parameters. In some sense, you can think about a fixed parameter algorithm is a way of somehow formalizing the arguments for backtracking algorithms or branch and bound algorithms. Great. So, but today we talk about more about approximation algorithm. Their running time should be polynomial time, but but these are not exact. So they are not exact in some sense. They are approximate solutions that we get it here. Okay. So that's about this one. Good. So let's now talk about maximization and minimization problems. Yeah. Okay. So that's about just actually give me 1 second. Yeah. Okay. So do you hear me well? Please unmute and answer.
Yes.
Great. Okay. So here about approximation algorithm in general. As I mentioned, it's a popular way to combat NP hardness. Actually, it was even more hot maybe 10, 20 years ago. Still, I mean, it is a part of the solutions for lots of problems. Whenever we cannot get the exact essentially answer, we try to get approximate solutions. So it still is popular, but maybe it was more popular or hot topic, I will say 10, 20 years ago. In some sense, because lots of important problems now we have a better understanding about their approximation, guarantee, what can we get it, what we cannot get it, etc. So here consider any problem X which belongs to NP. And the goal of that can be maximization or minimization. So here, in general, when we talk about maximization, it means that, I mean, the objective function is a maximization or minimization. So, of course, in one way, maximization and minimization, there is no difference for that. Because if you want to maximize a function f of x, you can always say minimize minus f of x, and vice versa. So these two are equivalent in some sense. In that sense, there is no difference between maximization and minimization problem. However, when we talk about maximization and minimization here, first we are talking about the natural objective is maximization and minimization, and the objective function is so the objective function is often positive. So that's very important for this kind of approximation algorithm. When we talk about maximization and minimization, we are assuming that the objective is positive. That's one thing. And the other issue is that generally in the objective function, we don't have minuses. Because if we have the minuses, this is again a typical thing, that if we have the minuses, so if you have the, I don't know, some cost, so say profit minus cost. So this is a typical objective function that somebody may consider for some problem. But the issue is that in this type of problem, when the profit minus cost is the problem, this approximation, the objective function can be very close to zero. Because profit and cost can be very, essentially tiny difference with like difference from each other. And when you take the minus, they become it can be very close to zero. Again, it's still positive, but it is it can be very close to zero. In that case, also, when we have this kind of negative thing in the objective function, they generally change the objective function to be, there is no negative there, like no minus there, because when there is a minus, actually this becomes zero, and it would be very hard to chase optimum. What's the meaning of that? It means that optimum can be very, very small, and then even if that's, so if it becomes, I don't know, something like epsilon, for very small epsilon, so this is the optimum. So optimum is the best solution that we can for this problem. If this becomes epsilon, then say if we have any approximation, even we have a log n approximation, it should be log n times epsilon, which can be still very hard to do that. Generally, if we have such kind of minuses, this is not a general proof, it is an intuition, then the problem is inapproximable, in a sense that there is nothing even better than order n approximation for the problem. When we say that the problem is inapproximable, is that if n is the input, we cannot get anything better than n approximation for the problem, n or larger. That is very bad approximations. So generally, when the objective function is like that, we are changing it to make it essentially positive. I may give you some example later on that. But so this is the two things that I have mentioned. Generally, the objective function should be positive, and it should be not also very close to zero. It means that it should be not something minus something. Generally, these are some integers, etc., that it should be can be far from zero, and then we try to minimize or maximize the problem. Any questions so far? So these are very important intuition when you work for any problem in the approximation algorithm, which is actually there are a very nice theory, lots of nice techniques here that has been designed for this problem. Okay. So when we consider an x of NP, we generally consider the optimum for this problem. So then we say that an algorithm that we have, as I mentioned, it should have polynomial time, running time. Otherwise, it would be useless, to have some algorithm which is still exponential. We want to get polynomial time algorithm. We know that these are NP-hard problem. So far, we don't have any polynomial time algorithm for them. Because of that, we are getting a polynomial time algorithm, which is not exact, but it is C approximation of the problem. So it is a C approximation if it has this property. So if it is a minimization, the cost of your algorithm over the cost of optimization, the best solution, opt of x means the best solution of x essentially, should be at most C. And if it is a maximization, is the reverse of that. Cost of the optimum over the cost of algorithm should be at most C. So this is important because in this case, C is always greater than or equal to 1. So it means that if C is equal to 1, then it is an exact solution. So if C is equal to is the exact solution, otherwise C would be greater than or equal to 1. Sometimes, some people so for minimization, it is always, this is the definition, that should be less than or equal to C. Some papers, they have been the case that they keep the same things for maximization as well. So for example, what is a maximization problem that I think we even talk about? It is the maximum matching. So you are given a graph and you want to find the maximum number of edges such that none of them share an endpoint. So there is nothing like this. So this is a matching problem. So in the matching, we try to find the maximum number of edges to do that. So if we have the maximum number of edges to get this one, then what will happen if we want to use the first things? So of course, in this case, the algorithm, because it's a maximization problem, it may so the algorithm, the cost of our algorithm, or the profit of our algorithm, or the number of edges in the algorithm. So number of edges in algorithm over the number of edges in opt. So in this case, of course, the size of the algorithm would be less than the size of opt, because opt is the maximum. So in that case, the people, and for example, there is a simple greedy maximal matching. What is a greedy maximal matching? That at each time, so you just have one arbitrary order of the edges, and then you are adding the edges one by one. And as long as you can add an edge, you will add it. This is a simple greedy maximal matching. And we know that this at least gets half of the optimum. So in this case, we know that the approximation factor of the, if we define it like this way, if it is alg over opt, like if we want to just keep the same alg over opt for both maximization and minimization, the approximation factor would be 1/2. Some papers, they mention it, but generally the way that the people are considering it is more like this one, that we always consider the one which is smaller at the top, the one that is larger on the top and a smaller one in the bottom, either it is the algorithm or opt, and then we get some C which is greater than or equal to 1. But there are some papers that they are also considering always this version of the problem. So the approximation can be less than 1 or greater than 1. But again, so in that case, in both cases, if C is equal to 1, it means that you have the exact solution. But with this definition, always we know that C is greater than or equal to 1. And when C reaches 1, it means that we have an exact solution. So it cannot pass 1. Does it make sense? Okay, so now that we talk about the maximization and minimization problem, I want to give you a general idea about the maximization and minimization problems here. So this is actually a very good idea, that you know what are the problems that are there and what are the classes that we have. So interestingly, so here and again, we talk about minimization problems. Each problem, the minimization and maximization can be the same if you put minus. But here we want to talk about natural algorithms that are maximization or minimizations. Actually, there is another way for maximization. So if you have some kind of, like if you want to maximize, f of n, the other case is that you can minimize c minus f of n. For a very large C, for a very large constant C. So if you have that one, this actually, or these problems also, or this, you can consider it very large C. It can be constant, or even it can be function of n. And then when you try to maximize this, you can minimize C minus. But this is the other thing that I don't, as I mentioned, that we don't like in approximation. We don't like minuses in the objective function. Generally, we have positive essentially functions here. And there is no such kind of minuses. So there are two ways that you can do it. But here, when we talk about maximization and minimization problem, we talk about problems which are naturally maximization. So it is, so these problems are naturally maximization or minimization. Good. So we talk about the problem which are natural maximization or minimization. Good. And let's start with minimization problem. Interestingly, for minimization problem, the classes of different classes, these are the things that so far we know. And the classes are many more actually for maximizations, for minimization comparing to maximization. So one class, like of course, sometimes C, the approximation, is equal to 1. In this case, essentially means that this is a polynomially solvable. So this is the polynomially solvable essentially. Good. Now, C can be essentially order 1 or theta of 1. So these are the problems that. What's the meaning of that? Generally, it means that we can get a constant factor approximation for these problems, but we cannot get 1. So this is the one that is called, essentially, this is APX hard problems. APX hard problem is the set of problems for which we cannot get exact, we cannot get exact algorithm, and we cannot be even close to exact algorithms. So for some problems, we can actually, maybe it is, let me just see that one. C can be 1 plus epsilon. For any constant epsilon greater than. So after C, so these problems that you can get 1 plus epsilon, where epsilon can be arbitrarily close. I mean, it can be constant. So you can get 1. You cannot get exact 1, but you can get 1.00001 or 1.00001. So you cannot get exact, but you can come arbitrarily close to exact. These problems are the algorithm for this problem. It is called PTAS. It is called polynomial time approximation scheme. Again, polynomial time approximation scheme. Those are the problems that we can get 1 plus epsilon. So for some problems, we can get this 1 plus epsilon. Not too many, but there are some problems, like, for example, Palladian graph, etc., that we can get such a thing. After that problem, this is the class that comes, and C is equal to theta of 1. For this problem, these are the problem that, so for the problem that we can say that there is no PTAS. So if you say no PTAS, and of course, no PTAS, all of them are under some complexity conditions. Then it is called APX hard. So if we can say that for the problem under some complexity assumption, there is no 1 plus epsilon approximation for arbitrary small epsilon, then this problem is called APX hard. So there is no PTAS. Lots of problems are like this. There are only very few set of problems on a special graph like planar graphs, or some problems like a knapsack and other type of things that for them there is some kind of simpler problem that for them there is a p-task. For lots of problems, this problem would be apx hard. It means that it would be theta of 1. It means that there is some constant. Maybe the constant is small, but we know that definitely we cannot get anything better than this approximation for the problem. So no approximation better than above. So no approximation better than above unless P is equal to NP. So what are the set of problems? I cannot define all of them. You can actually, these are some of them that I mentioned. You can actually search this one. All of them are very famous and classic problems. And you can get the exact definition in Wikipedia or other, I mean, you can get it everything online. So I just mentioned some important one, but not all of them because that takes a lot of time. And we may not have that one. So after this, so this we have talked about the C equal to this order 1. So for this problem, there is some constant, I don't know, 2 approximation, for example, 1.5 approximation, 1.4 approximation. And we know that for some small epsilon, like there is nothing better than 1.00001 approximation for that. This might be very small comparing the approximation that we know, but we know that you cannot get 1 plus epsilon for arbitrary small epsilon, which is called the p-task. So these problems are APXR. So what are these problems? For example, a famous problem is Steiner tree. So what is a Steiner tree? A Steiner tree is a generalization of a spanning tree. So you are given a graph and some vertices in this graph are called terminals. And there are some other vertices that can be, it is just a regular vertices of the graph. And this is, I mean, they can be a Steiner point. And so there is some distance is given to you. So any edge has some length here. And what is the goal? The goal is to buy the I mean, it can be some edges even between these guys. The goal is to buy. So you want to buy minimum cost. So you want to buy you want to buy a set of edges with mean cost So you want to buy a set of edges with minimum cost to connect all terminals. To connect terminals. So as I mentioned, these are the terminals, and you want to connect these terminals by buying a set of edges. This is a Steiner tree problem. This is a generalization of a spanning tree problem. In the spanning tree problem, every vertex is a terminal vertex. So we want to connect all vertices of the graph. Here you want to connect only the given set of vertices, which are the terminals. So a generalization of this problem, it is called a Steiner forest. So for this Steiner tree, for example, I mean, there is a lot of work. So there was approximation. So there is a simple algorithm that gets essentially 2 approximation for a Steiner tree. So for a Steiner tree, let me just give this one. So here for a Steiner tree, there is a simple two approximation. So what is this one? So essentially it is like that. So these are the set of terminals. Just find the shortest path between any two terminals and connect them. So these are the all shortest paths. So find the all shortest path between the terminals and then find the minimum spanning tree in this new graph. So minimum spanning tree in this new graph. So that's essentially the whole algorithm. Find just between any two terminals, find the shortest path and then find the minimum spanning tree. Minimum spanning tree, of course, we know that there are several algorithms. There is a Borufka, Kruskal, and Prim. All of them give essentially the exact solution for that. So you can show that this is it's not hard to see that this is actually a two approximation for the problem. So whenever somebody gives you some vertices of the graph that you want to connect, how can you do that? You can just find the shortest path between this set of terminals. Then you will create a new graph that the only vertexes are the set of terminals. You will remove all other vertices. And between any two terminals, you are putting essentially an edge whose length is the shortest path between them. Then in this new graph, you are finding a minimum spanning tree. And that gives you actually a two approximation for a Steiner tree. Good. So that is one. I just mentioned this one, such that you know some algorithms there. So in the there is another problem essentially. So we are talking in the C is equal to 1, C is equal to 1 plus epsilon, and then we are talking about C. For this is another problem, Steiner forest. What is the Steiner forest? So in the Steiner forest, you are given so instead of giving the terminals, you are giving pairs of vertices. So we call it S1, T1, and then S2, T2. The objective is, again, very similar to a Steiner tree. So you want to buy a set of edges such that all these pairs that are given to you, they are connected to each other. So what's the difference? The difference is this one. If this is the graph, this is S1, T1, and then this is S2, T2. Say if this is the graph that is given to you. So if in a Steiner tree, if all of them are the terminal, you need to buy essentially the whole graph such that they are connected. But in a Steiner forest, no, you can only buy this set of edges and this set of edges. And say all of them. So this is 1, 1, I don't know. This one is 10, this is 1, 1. Because here S1 should be connected to T1 and S2 is connected to T2. So this problem also, there is a two approximation for that. It is relatively simple. This is one of the problems that if you get anything better than 2, I mean, in the abstract of the paper before submitting to the conference, you can, in advance, you can thank them for giving the best paper award to your paper. So it's a very famous problem. The people tried, and this is a very important one to get better than 2 approximation, but so far there is no better than 2 approximation for the problem. By the way, for a Steiner tree, actually, interestingly, this simple one that I have mentioned to you, it is 2 approximation, but there's a long set of work starting from 2, then I don't know, 1.99, 1.97, and currently this is the best one is 1.39. Generally, this problem, the lower bound is very low. I don't know, it is maybe 1.1 or something like this, essentially hard. So there is a big gap between the current inapproximability and the approximability of the problem, but we can get 1.39. This was I think it was a paper in Stock 2010, which got the best paper award. This is for the Steiner tree problem. But for Steiner forest, we don't know anything better than two approximation. There is a simple two approximation, and we don't know anything problem. So there are several other problems I will just mention. So I have defined, for example, a Steiner tree problem here. And note that Steiner forest, it is defined here, is a generalization of a Steiner tree. Why? Because in a Steiner forest, so if in a Steiner forest, we say that all these terminals should be connected to one particular terminal. So it means that essentially, so all the pairs that we have it are something like this. So here we want to connect this set of terminals. So we can say that this is for a Steiner tree. That we say that all these terminals should be connected. To make it a Steiner forest, this is some kind of reduction actually between these problems. So we can solve a Steiner tree with a Steiner forest. How? So instead of doing that, so that this is the first pair is S1, T1. Then this is S2, T2. So T2 is always equal to one vertex. Then this is S3 equal to, like this is T3. So all the terminals are the same. Then this is finally S4. This is equal to T4. So we know that all of these guys want to connect to this case. So this is some kind of reduction from a Steiner tree to a Steiner forest. It says that essentially a Steiner forest can solve a Steiner tree problem. Is it clear? This is important. The reduction here. Okay, so that sounds good. Here, so this is for Steiner tree and Steiner forest that I have mentioned. There are other problems, traveling salesman problem. So for this problem, what is the goal? The goal is to, I mean, these are very classic problems. So you are given a set of, essentially, you can think about that you want to find a tour that goes through all vertices of the graph and come back to the first things. And here, I mean, you may go to one vertex more than one if it is needed, but the goal is that you want to go, you have essentially traveling salesman problem, that one travel, like this is essentially salesperson that needs to go to all places in a city and come back to his home at the end of the night. And you want to find the minimized, essentially the total distance that this guy is traveling. This is for TSP problem. For this problem, actually, I mean, very recently, there is this was again very big, important problem. And there is, I think that was last Fox, that there is 4.9999 approximation is known. So a little bit better than 3/2 is known. So it was a big problem whether you can get better than 1.5 approximation for this problem or not. It was a long time. And this was, again, this paper also got the best paper award in, I think it was in Fox or Stock recently. So it was a year ago or something like that. So this is a 3/2 minus approximation, 1.5. Again, 1.5 is very simple for lots of these problems. 1.5 is very simple algorithm essentially for this problem that again uses essentially a spanning tree plus some additional edges, which is a matching. But getting better than 1.5 was an important problem. And this is like and these are so classic problems that when you write the abstract, we are just improving you can see the abstract of the paper is that say that we are just improving the TSP approximation in this paper, period. You don't explain anything about motivation, anything, because these are so classic problems. Good. So there is another problem. So for this one, I mean, again, the hardness is much lower. There is a vertex cover problem. That's also is an important problem. So let me just mention the vertex cover problem. So what is the vertex cover problem? So vertex cover is that this is also very classic problem. So for TSP, there is something a little bit better than 1.5. And again, this problem is apex hard, means that the hardness is 1.001 or something like this. Some small things. But for vertex cover, this is the problem. You are given a set of vertices. So you are given a graph. You want to find the minimum number of vertices such that each edge that you are considering in the graph, at least one of the endpoints in the set. So each edge has an endpoint in vertex set, in the vertex cover essentially. So this problem, it is called the vertex cover problem. And for this problem, there is a very simple, again, two approximation. There is a hardness of 4/3. So we can say that you cannot get better than 4/3 unless, so no better than 4/3 unless P is equal to MP. But also there is other things under unique game conjecture that we discuss next time that says that no better than 2 even. So for this problem, there is a simple algorithm, but we don't, and we can say that under some complexity assumption, there is nothing better than 2 for this problem. There are other problems like facility locations that I think you can just see the definitions in Wikipedia. All of them, I mean, the people worked a lot on this problem to get the exact constant. For the facility location, also the hardness is close. So as I mentioned, for some of these are close, the hardness. For example, for vertex cover, we know that you cannot get better than 2 approximation even. And there is a simple 2 approximation. For facility location, or also the upper bound and lower bounds are very close, but they are not exact. Still, there is some gap. And once in a while, somebody finds and a little bit improves generally the approximation algorithm, sometimes the hardness. Good. So these are the problems that are all in the class of C equal to theta of 1. So let me clear these things. Okay, so after this class, there is another class which is, so this is again, C equal to 1, C equal to 1 plus epsilon, then C equal to order 1, or theta of 1 even. Then C is equal to theta of log star n. So what is C of log star? So log star essentially means that, so log star is much smaller than log. It's a very small growing function. It is somehow comparable with the Ackermann function. If you search Ackermann functions, this log star is behaving very similar to Ackermann. I think that is the inverse Ackermann function. So Ackermann is going very fast. The inverse Ackermann is going very slow. So this goes very slow. So what is the definition of log star? It is the, so this is how many times you will take the log of essentially. So define log I as the, you are taking the log I times. So log 1 of n is log 2 of n. And then here, log I plus 1 inductively is log of in. So for example, log 2 of n. So log 2 of n. So this is not power. So it means essentially log of n. And log n is by itself is a small things. And then log is almost essentially constant for any practical purpose. But this log star is even smaller than n. So log star n is defined to be the least integer such that if the log n of I is less than or equal to I. So how many times I will take the log of these guys to become essentially less than 1? And this is a very small growing function. It is, I mean, still increasing function, but very, very small growing. So it is like, you cannot imagine that, like as I mentioned, for all practical purposes, if not log n is enough, but log n is already very small. So it's a very good approximation. It is almost like constant. But this is even much better than that. It is very small. So the minimum number of I for which log n I is less than or equal to 1. And and this is actually a problem. It is called asymmetric case-center problem. So what is the asymmetric case-center problem? So you are given a directed graph. So it is a directed graph. This is the reason that is called asymmetric. So directed means essentially directed means asymmetric. Maybe just use it. So what is the goal? So the goal here is that you want to find a set of, so you want to open case center here in this graph, and each vertex should go to one of these case centers. And what is the goal is to, you want to make sure the maximum distance from, so you want to minimize, but this is some of the centrality problem, minimize the maximum distance from a vertex to its center. So again, you want to open case center. That's the thing that is called case center problem. You want to open case center means that you want to select k vertices of the graph such that each vertex should go to one of them, like essentially to be served. And it should go and pay the distance from that vertex. So if this is this vertex here, it maybe needs to go to here. This other vertex may want to go here. And you want to find so these distances that you are considering, you want to make sure that the maximum is minimized. And also one other property that this graph has, this property has this triangle inequality, even though it is directed. So what's the meaning of that? So it means that it's directed. So if you have two vertices A and B, so if you go from A to, if go from A to B, the distance might be different from B to A. So these two are not necessarily equal. That is the thing that's asymmetric. However, still it has triangle inequality. What is the meaning of triangle inequality? It means that if you go from A to B, and then from B to C, then the distance that you will go should be larger than A to C. So we have this triangle inequality. This is the case, and this is essentially asymmetric case center. For this problem, the best algorithm, it is known, and this is also tight, I believe. This is also log star n. So this problem is known essentially that has the log star n. Good. So, and again, these are some of the assumptions for these classes. So these are the problems which are well known for this one. If you have your own problem, you want to see how hard is that, you need to compare with one of these problems that you have seen here. Good. Let's go to the next problem. So the next problem is the log n approximations. So the log n is there are some other things like, for example, square root of log. So we talk about essentially again. So we talk about order 1, then order log star n. There are some problems which are order square root of log n, but less. You can search, you will find it. I think some cycle cover problem and others that you can find, these are square root of log n. Then the next very natural one is log n. So what are these log-n approximation? The main problem is set cover problem. So what is the set cover problem? So the set cover problem is that you are given a bipartite graph. And these are the sets. These are the elements. And each set contains a set of elements. You want to find the minimum number of sets to cover all elements. What's the meaning of that? It means that here, you want to essentially find a set of this minimum number of sets such that their union is all the elements. This is a set cover. And for this problem, also we know that the best algorithm is actually log-n, even better than that. So we know that it is ln of n, the best approximation for this. And it is no approximation better than ln of n unless p is equal to np. So that's a very tight result. That's important as well. I think it was under some other conditions, but then I think the final one is p not equal to np. And by the way, n is the number of sets here, or the maximum number of sets and elements in this problem. So this is a set cover problem. There is a node-weighted Steiner tree. That's another problem. What is a node-weighted Steiner tree? So the node-weighted Steiner tree is this problem. So the same Steiner tree problem that I have mentioned, that you want to connect essentially a set of terminals are given and you want to connect them. But here, instead of buying a set of edges, you are buying a set of vertices. So for example, in the, these are the set of terminals, in the Steiner tree, and this is one vertex here, in the Steiner tree version of the problem, you needed to buy all these three edges. But in the Steiner tree, regular one, but node-weighted Steiner tree, you only need to buy this vertex. Then all of them will become connected. So in some sense, the edges are coming for free. This problem called node-weighted Steiner tree, this is also log-n hard problem. As we mentioned, so these are the weights on the edges. Then what about after these problems? Let me just. So there are several other things that you can see. The other problem after that, this is actually lots of this Steiner tree plays a very important role here. The other one is log-n to the 2 problem approximation. What is log-n to the 2? This is the for group Steiner tree problem. So this group Steiner tree is exactly like a Steiner tree. So it's very similar to a Steiner tree. However, the issue is that instead of, so these are the terminals that was in a Steiner tree that is given to me that I need to connect. Here in the group Steiner tree, so I have, instead of one terminal, so I have, so for this one, you might have several vertices here for this one terminal. And for this other, this is the group. So for each essentially terminal, you might have several groups. So this is one group, this is another group, this is another group. These are the set of vertices. And what is the goal? The goal is to connect, again, by a set of edges, such that you will connect one vertex from each group. That which vertex is up to you. So you want to buy a set of edges. Again, these are different groups are giving to me. They can possibly even intersect. So this vertex might be also this vertex of this. This might be another group essentially. So a set of groups are given, say, with different colors, and you want to find a set of edges. that you will connect one vertex from each group. So in some sense, you can consider that these red guys or these green guys are already connected somehow by some background network. And as long as one of them is connected to others, I will be happy. This one you decide. This problem is actually log n to the 2 approximation. There is a log n to the approximation, and is it log n to the 2 approximation hard? There is another problem, log n to the epsilon for any constant epsilon. And the hardness is still log n to the 2. This is a directed Steiner tree. What is a directed Steiner tree? It is exactly the same problem as before. So these are a set of terminals that are given to me. But the whole graph is directed. And in this directed graph, you want to connect essentially all terminals. So the graph is connected. You want to connect all terminals into one particular terminal. So this is the sink. So one terminal is given, the other, essentially all terminals are given to me, and I want to connect all of them into one terminal. This is called directed Steiner tree. For this problem, there is an n to the epsilon for any constant epsilon, and the hardness is log n to the 2. And so that's another problem that it is a bit next level. Then after that, there is this set of problems. It is called a label cover problems. So there are this problem, label cover problem, which is n to the epsilon hard. Sorry, n to the 1/3 is known. Actually, this is our result. But the hardness is 2 to the log n to the 1 minus epsilon. Note that if it was 2 to the log n to the 1/epsilon, then this problem would be n to the 1 minus epsilon. But these are not like that. It is 2 to the log n to the 1 minus epsilon. So this actually, this is less than any n to the epsilon hardness. So log n to the 2 to the log n to the 1 minus epsilon is actually less than. So it is, I will say, is little o of n to the epsilon. We have such a hardness, and this essentially upper bound n to the 1/3 for this problem. You can say this problem, the directed Steiner forest, is actually a special case of this problem. So the hardness actually comes from that problem. But this is directed Steiner forest. So this is again a Steiner forest. It is the same as a directed Steiner tree, unless that we are given a set of pairs that we want to connect. Next problem is this hardness class. It is order n. So this is the definition of label cover is mentioned to the note, and we will talk about it later. But this other things is coloring. So finally, this is the latest class. So for this class, essentially the hardness is n to the 1 minus epsilon. So it means that, and the approximation is order n. The sense is that there is nothing better than n, you can get it. So what is this problem? Is the coloring problem. So you are given an undirected graph. You want to find a minimum number of colors of vertices such that every 2 adjacent vertices have a different colors. So this is the graph that is given to me, and you want to color it with the minimum number of colors, for example. So if it is the case, for example, you can maybe color these 2 vertices both red, and then this guy yellow, and then maybe this guy. So this is, so the minimum number of colors to color these vertices. Again, 2 vertices that they have an edge, their color should be different. So that the minimum number of colors you want to find it, this is a coloring. So for this problem, is the best approximation is order n, and we know that you cannot get better than n to the 1 minus epsilon. So what's the meaning of that? It means that in general, if a graph of n vertices are given to you, I mean, a simple approximation is that to just color each vertex a different color. We don't know anything better than this essentially for the solve. That's the best approximation that we have for this problem. So we have a different set of classes of problems. Again, as we discussed, we have like one approximation, 1 plus epsilon. So we had 1 plus epsilon. Then we have this order 1. Then we had log star n. As I mentioned, there are some problems which are square root of log n, but then we have log n. Then we have log n to the 2. Then we have, I think, n to the epsilon for any constant epsilon. Then we have n to the 1 over 3. And then finally, we have order n. So this is a large set of classes that we have for minimization problem. For maximization problems, actually, is a bit, we don't have that many classes of natural classes, at least. So in general, it was known that for maximization problems, either you have order 1 approximation. It means that either we have, I mean, of course, there is still p-tasses. So we have 1 approximation, 1 plus epsilon. These are p-tasses that we discussed. But other than that, either before it was generally known that for maximization, either there is a constant factor approximation, or generally this problem is order n hard, like a coloring problem. So that was there, unless, I mean, for example, there are some famous problems for maximization problems. So this is the maximum coverage problem. What is the maximum coverage problem? So you are given, so the maximum coverage essentially is the input is the same as the set cover problems. So you are given essentially a set of elements considered bipartite graph. And so this is the sets that are given to you. What is the goal? You want to find so you want to select. So these are sets. These are elements. You want to select K sets. K is also given to you, which maximize, we say to maximize the union. So what is the goal? You want to select K sets such that their union is maximized. For this problem, actually, this is a famous problem that for this, I think the approximation is 1 minus 1 over E approximation for the problem. It's a constant factor. Another problem is the max cut problem. So you are given a graph and you want to, so this is a graph and you want to essentially partition the vertices into A and B such that the number of edges in between is maximized. So the number of in between is maximized. For this problem, there is a very simple algorithm that it is a 2 approximation. How can you do that? Each vertex goes to A and B at random, essentially. With probability 1/2, it goes to A. With probability 1/2, it goes to B. If you consider each edge, the chance that this edge is in the cut is exactly the probability would be 1/2. Why? Because one vertex should be in A, the other vertex should be in B. And then 1/4 for each of these possibilities. So if there are 2 vertices, so if this is A, B, so there is a 1/4 that A belongs, so this is, say, essentially U and W. So there is a 1/4 that U belongs to A and W belongs to B, and 1/4 that W belongs to A and U belongs to B. So this is 1/4 plus 1/4 would be 1/2. So in expectation, each edge we will get it with probability 1/2. So this is a 1/2 approximation, but there are something better than this for this problem using a semi-definite programming that can get better than 1/2 approximation for the max cut. But again, all of them are, by the way, 1/2 here, I mean 2 approximation. Whenever you will see some number less than 1 for maximization problem, if you want to get the approximation, you need to consider the inverse of that, 1 over that number. Okay, so that was this one. Then the other problem, these are, so in this one. As I mentioned, so we knew about order 1 approximation for the problems, lots of problems. Then we knew about hard problem. Lots of other problems were essentially order n hard. So what is the order n hard? So this is the independent set problem. So you are given essentially graph. You want to find the maximum set of vertices such that there is no edges in between. So no edges between these vertices. And you want to find the maximum number of set of vertices. This problem called independent set. And I mean, it is, again, you can give a simple reduction from independent set to clique. What is a clique? The clique exactly the same problems, but then you want to make sure that you want to find the maximum set of edges, maximum set of vertices, such that all possible. So this is a complete graph. All edges are there. You can see there's a simple reduction from independent set to clique. Why, if you have a graph is given to you, just get the complement of the graph. Every edge which is there, just don't put it, and every edge that does not there, just put it. So if you take the complement, so this is the clique, and this is independent set. So it is independent set. And as I mentioned, if you take the graph, the complement of the graph, so independent set and clique would be essentially the same. Good. Now, there are then later some other problem it is mentioned. So there is this label cover. Label cover is a problem that has two problems. It is called min rep and max rep. I think the definition is here. For the max rep, for these problems, again, the hardness, this problem later has been done. It is order n to the 3 we know as the upper bound, and 2 to the log n to the 1 minus epsilon. So using label cover, you can get something better than n, but still it is all very bad. Generally for approximation is something worse than log n. It is not that, maybe polylog is the best that we can tolerate. After that, the approximation factor would be very bad. But another problem, which is that actually, this is one of them that we had, this is a very natural problem again, that is known, and it is more recent essentially, that is known that this problem actually is a log n hard, or like in the polylog hard. This is the unique coverage problem. What is the unique coverage problem? Again, the input is a set cover problem. So these are the sets, and these are the elements, and each set contains several elements. What is the goal? You want to find, so here, you want to find, select a set of these sets. I don't even say how many, it's up to you. You want to select a set of these sets such that maximize number of uniquely covered elements. So what's the meaning of that? So a set, so an element is uniquely covered if only one of these sets, essentially, it is contained in exactly one of these sets. So what is the goal? You are given a set, you want to select some of these sets such that you will maximize the number of uniquely covered elements. Again, what's the meaning of that? You want to select essentially a set of sets such that those elements that are exactly in only in one of these sets that you have selected, these numbers are maximized. For this problem, again, there is a simple log n approximation for that. But this problem is log n to the epsilon hard, and there are some other things that are there. I mean, there are better improvement on the hardness. Still, it is not a tight answer, log n, but I mean, the belief is that it should be, this problem should be log n hard as well. But we don't have the tight result, but we have a, I mean, this, but it is at least not a constant under some complexity assumptions. So this is, again, so this is very similar to this maximum coverage. In the maximum coverage, you want to select K sets such that you will maximize the number of elements that are in the union, maybe covered. Here, the only difference is that, of course, there's a K version of that you want to select K set, but here I don't say even how many sets. You can select any number of sets. It can be like just one set, or it can be 10 sets or all sets. But the goal is that you want to maximize the number of uniquely covered elements. There is another problem, domatic number, which is essentially you want to find this problem, maximize, like you want to partition the vertex set such that each vertex set is a dominating set. And you want to maximize this set. This is another thing actually Arvind Srinivasan, who is a professor here at UMD, he actually done this. So this problem, the unique coverage, that's my work, and this one, the domatic number, is actually Arvind's thing. These are the only two natural problems that we know that these are actually log n hard maximization problems. Good. So let me just see. As I mentioned, for some problems, like for example, for planar graphs, lots of these problems, there is a p-task for them. So for planar graphs, lots of these problems that we have mentioned, for example, a Steiner tree, Steiner forest, lots of these problems, they have 1 plus epsilon approximation for any constant epsilon, for any epsilon greater than 0. I mean, it can be constant, sometimes it can be up to 1 over log n as well. So for planar graphs, some special graphs, actually there is a better approximations. But still there are some problems. For example, even for planar graphs, there is this coloring problem. This coloring problem, as I mentioned, there is nothing better than order n approximation in general graphs. But for planar graphs, it is only 4/3 hard, essentially. And finally, there are these two important problems that I have mentioned here about so this problem, these are again, this 1/3 for the min rep and max rep problems. These are actually related to some unique game conjecture. So in general, what is this label cover problem? So in the label cover problem, you are given a bipartite graph that has A1 to AK, and this is B1 to BK. What is the goal? The goal is that so in the min rep is this, max rep is this one. You want to essentially select only one vertex from, so you have a partition of these vertices into A1 to AK and B1 to BK. So you can consider that there are n vertices above, so n vertices here, n vertices here, and k is equal to a square root of n. So what is the goal? The goal is that you want to select only one element from each of these sets, K sets, such that you will maximize the number of edges in between these selected vertices. This is a problem which is called max rep. And as I mentioned, for max rep, there is what is the best approximation? The best approximation that we have it is n to the. So for this one, the best approximation is n to the 1/3. And the hardness that we have it is 2 to the log n to the 1 minus epsilon. There is a minimization version, min rep. It is very similar. So the idea is that there you want to select essentially more, you can select more vertices from each vertex, but you want to find the minimum number of vertices that you can select it such that you will cover all super edges. So that's the definition that you can actually see it here and in the book. This min rep and max rep, they have the same hardness of these problems. And these are some important problems like the all unique game, etc. It comes from these problems. Even this problem, when the graph between these guys has some special structure, there is the same hardness holds, unless the case that for each of these, if you consider any AI and BJ, if this problem essentially only between any of two there is a matching, then this problem essentially becomes unique game conjecture, and the hardness then it drops from this n to the 1/3. And we don't know the hardness of this unique game conjecture. That's the thing that I think Professor Pilgasash talks more about it next week. But anyhow, these are some of the different classes of minimization and maximization. These are like very natural classes that if you have some problem, you want to see whether how hard is that. In some sense, you need to use, these are more assumptions that I have mentioned. So you need to give a reduction from one of these problems. Say, okay, this is maybe log n hard, then you may consider set cover. If it is constant, maybe you want to consider, I don't know, if a maximization problem, you may want to consider the maximum coverage or max cut or other things. So these are somehow the assumptions. These are the problem that is hard. These are, I mean, very classic problems. If you have a problem, you want to see how hard is it, you need to compare and see which of these problems is correct, the closest problem to that. Then you can get some hardness from that and possibly use the ideas of that problem to get a hardness result, to get an approximation algorithm for that problem as well. So we will continue about approximation algorithms next week. And yeah, and we have the presentation on this coming Thursday of all groups. Any questions? Good. So if no question, I think we can just stop share, and then we will continue next week. Okay. Have a good day. Bye for now.